It's going? Okay, so today we're going to find the moment of inertia of a hollow cylinder, which would be look something like this. Excuse my drawing, it's not drawn to scale, obviously. Yeah, I'm a really bad artist. Okay. This is going to be R. This is going to be big R. So the moment of inertia is defined by the equation R squared dm, where dm is a change of mass. So obviously to integrate this, we're going to have to find a dr, and something similar to equivalent of dm in terms of dr. So dm is change in mass. So the change in mass for this would be rho dV, the density of the cylinder times the change in the volume. So in order to do this, we're going to take a small piece of our cylinder, and we're going to take it out and roll it out. So when we roll out that small piece, it's going to look like this, where the height would be L, and the length would be the circumference of the circle, which would be 2 pi r. And this thickness would be dr. So now we can have rho dV, where dV would be the change of this volume. So change of dV is going to be equal to the length times dA, change in area, and that's going to be equal to 2 pi r L dr, and this is going to be our dm. So dm is going to be equal to 2 pi L dr. So now we can substitute this equation into our integral equation, and that will give us, and then the limits are going to be from little r to big R, obviously. And it's going to be r squared dm, which is 2 pi L dr. And since this is a constant, you factored it out? I forgot the r here. 2 pi r. So we're going to take out the 2 pi L outside. So we're going to have 2 pi L r, big R, to r times r squared times r will be r cubed dr. And that will simply be 2 pi L. The integral of this would be 1/4 r to the 4, big R to r. And I forgot, of course, rho. Rho 2 pi L. Okay? So once we expand this, we're going to have rho 2 pi L times 1/4 r to the 4th minus 1/4 little r to the 4th. And we can simplify this by knowing that what rho is. So rho is equal to mass over volume, where this is going to be mass over our volume of our hollow cylinder, which would be simply the volume of the whole thing minus the volume of the inner cylinder. So that would be pi r squared minus pi r squared. This could be little r. Right? So then we're going to factor out the L pi. So we have L r squared minus r squared. So we plug this into rho. So we're gonna have mass over L pi r squared minus r squared times 2 pi L times 104 r to the fourth minus 1/4 r to the fourth. L's cancel, pi cancels. So we're left with m 1/4 r to the fourth minus 1/4 r to the fourth divided by r to the squared minus r to the squared. So we gotta factor out 1/4 and then times the 2, which will make it 1/2. Okay? So now this expression we can reduce by doing we could factor this. This will give us r squared minus r squared times r squared plus r squared, and then you'll have 1/2m, and we'll have r squared minus r squared. This will cancel, and that will give us simply 1/2 m r squared plus r squared, big R plus an r squared, and that will be the moment of inertia of a hollow cylinder. That'll be all.